this is a question from 2020 Life Sciences Biochemistry, question number 7. And it states that a globular protein of molecular weight 50 kilodalton exists as a mixture of monomers and dimers in solution. The most appropriate technique for the separation of these two forms of the protein is thin layer chromatography, ion exchange chromatography, gel filtration chromatography, or paper chromatography. This is a multiple choice question, which means you have only one answer. MCQ type. Would you try to answer? Okay. 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 You are correct. The answer is gel filtration chromatography. So we will discuss it in more details. So first of all, these techniques which are mentioned here, the first one is thin layer chromatography, but this one. This is a thin layer chromatography. So what is the, do you know like what is the principle of thin layer chromatography? Yes. Yes. Okay, quite right. So actually there is a mobile phase and we have a sample. So these sample, usually proteins are not used for like in this kind of a thin layer chromatography. This is mainly used for chemical samples. So if your sample contains many compounds, so you put a drop of this sample on this TLC plate. So one thing is that this TLC plate is usually made up of silica, or it can be of other metals also. So this TLC plate, we put a sample on it, and there is this mobile phase, and there is this what we call the solid phase, right? And the sample will have different compounds. Suppose it has different compounds, so these different compounds will have a specific affinity for the mobile phase. Okay, so depending on that affinity, the samples or the compounds in these samples will be separated. So if you put a drop here, it will migrate towards this upper side, and the migration will depend on the affinity of the sample towards the solvent front, towards the solvent. So it will form a solvent front, and you can see the separation. So that is thin layer chromatography, which is a very simple type of chromatography that is often used in for chemical samples. For some pharmaceutical samples, we can also use this thin layer chromatography. Now the second option is ion exchange chromatography. So coming to ion exchange chromatography, this is a chromatographic system where we usually use proteins. So we use to separate proteins depending on the charge of the proteins. So this is an ion exchange, which means the protein will be an ion, either a cation or an anion. So depending on the charge of your protein, you will use either cation exchange chromatography or anion exchange chromatography. Okay, so what is the difference between these two? So suppose you have a mix of proteins, okay, and from that you want to separate your protein of interest. And now the question is, okay, just 1 minute. Okay, so you have suppose your protein is positively charged. How is it positively charged or negatively charged? So all proteins have this thing called pi, right? What is pi? Pi is its isoelectric point. So it is the pH where the protein will be neutral, or it will not have any net negative net charge, not negative, not positive. So pi is the isoelectric point of the protein, and if it will depend on the pH of the buffer that you are using. So if your pH is greater than the pi of the protein, then the protein will have a specific charge. If your pH is less than the pi of your protein, then it will also have a specific charge. Can you tell me whether the protein will be cationic or anionic in these conditions? If your pH is greater than the pi of the protein, okay, and if your pH is less than the pi, very good. So if your pH is greater than the pi, then it will lose the hydrogens, right? So what will make that will make the proteins cationic. And if your pH is less, it will retain the hydrogen, so the protein will be anionic. So depending on that, if your protein is cationic or if your protein is anionic, so you must know the pi of the protein and also the buffer pH that you are using. So depending on that, you will be able to know that if your protein is positive or negative. Now if your protein is positive, then what exchange chromatography that we should use? If your protein is cationic, and what is the matrix that we are going to use? Okay, if your protein is cationic, then which exchange chromatography we are going to use? Cation exchange or anion exchange? Yes, if your protein is cationic, we are going to use cation exchange chromatography. If your protein is anionic, we are going to use anion exchange chromatography. And in these cases, like if it is a cation exchange chromatography, the matrix will be negatively charged, and if it is an anion exchange chromatography, the matrix will be positively charged. Okay, so the matrix has the opposite charge, so that the proteins can bind to the matrix. So for example, here we can see that this is a cationic surface, immobilized. The cations are immobilized on this surface, and there are mix of proteins. So here obviously the negatively charged proteins will bind to the anionic proteins will bind to the cationic surface. So the negatively charged molecules bind to the immobilized cation surface, and what happens is that the positively charged proteins, they all come in the flow through, right? So flow through is the portion which comes does not bind to the column. Okay, that is the flow through. The positively charged proteins will come out, they will not bind to the column. Now your protein of interest, suppose it is anionic. Now it has bound to the column, very good, we wanted that, but now you want to separate the protein also. I mean, you will want it to come out of the column so that you can use it, right? Because your separation has happened, you have separated your protein, but now you want to collect it, right? So how do you do that? You add elution buffer. So this is called this is the elution stage of your chromatography. So what you actually use in elution buffer is a high ionic strength salt. So suppose NaCl. So we can use 1 molar of NaCl, and NaCl will have these negatively charged chloride ions, right? So these chloride ions will have much more affinity because it is much more negatively charged. So what it will do, it will compete with your protein. So the proteins, that is also anionic, but its strength of charge is much less than the chloride ions, right? So now the chloride ions will compete with your protein, and it will actually displace the protein from the column. So the chloride ions will compete with your protein, and it will displace your particular protein from the column, so that now your protein will come in the elution fraction of the chromatography. Okay, so the protein is now eluted out. Now there is one other thing also, like suppose you have a protein sample, suppose you have lysed a cell and you have collected the cell lysate, and there will be thousands of proteins, and of course along with your protein of interest there will be other proteins also, which will also be anionic. So all those proteins are going to bind to the column, and all those proteins will come out in the elution. So then how will you segregate your protein? So that is why it is shown here that it will form different peaks, but it may also happen that in this particular peak there are 2 or more proteins which are coming out in one particular ionic strength of NaCl, right? So usually what we do for purification, for further purification of the protein, we combine ion exchange with another protein purification procedure or chromatography procedure. Okay, so suppose we know that our protein is cationic, so we first use cation exchange chromatography, and then we follow it with either it can be gel filtration chromatography or it can be some other type of chromatography procedure, right? So that the protein can be further purified and further segregated from other contaminants, right? So that is the basis of ion exchange chromatography, and this is how the elution curve will look like, right? Okay, now coming to the next one, which is the gel filtration chromatography. The gel filtration chromatography is very much dependent on the molecular weight and the size of the protein. So actually in this gel filtration column there are beads, and the beads are not the important thing. The important thing is the pore size of the beads. So something you had missed while saying this, that you must remember that not the beads are important, but the pore size of the beads are important. Okay, so what pore size it has, and that will actually help you to separate your protein. So you have a mix of proteins, they are of different molecular weights. That can be it can be a large protein, it can be a small protein. Now there are some pores in these beads, and now these beads, in the pores of these beads the small proteins can enter, okay, but the larger proteins, they will not be able to enter in the pore size, in that particular pore size, in the particular pores, right? So that is why pore size is very crucial. So you have different columns or column matrix which has different pore size. So depending on your size of the protein, you have to select the column which will have, or you have to select a matrix which will separate your protein. So now you have these beads, you have these pores where the small proteins can go into these pores, but the large proteins, they will have a difficulty in going into these pores. So therefore when we pass buffer through the column. First we have loaded the protein on the column, and then when we pass buffer through the column, the larger proteins will come out first. You can see these large proteins are coming out faster because they cannot enter into the bits, so they will come out faster. Okay, so therefore the larger molecular weight proteins will come out faster, whereas the smaller proteins, you can see the smaller proteins are inside the bins. Okay, so these smaller proteins will also come out, but at a later stage of elution. So you are passing buffer and the smaller proteins will come out later. Okay, so that is how you're going to separate your proteins according to your molecular weight. Now coming back to the question which was asking, like, how do you separate a protein mixture which have monomers and dimers? So the protein was of molecular weight 50 kilodalton. So if the protein dimerizes, then the protein size will be 100 kilodalton, right? So now the 50 kilodalton and the 100 kilodalton proteins can be easily separated by this kind of gel filtration chromatography, because the dimers, they will have a larger size and they will come out faster in the gel filtration chromatography. So they will form a curve first in the elution profile, and then the smaller proteins, they will come out later. So the monomer is going to come out later. It is going to give you a peak or a like curve later on. So that is how you separate the proteins according to their molecular weight, and this is actually a very good method for separating out your monomers and dimers. And if the protein forms oligomers also, like trimer, tetramer, that also can be separated from this kind of chromatographic system. But you also have to remember that you have to select the right pore size. So usually these matrix, they have cutoffs. Okay, so for example, there are these columns which are one more thing, that is these columns usually have this Safarow's matrix. Okay, so these can be S200, S75. S stands for Safarow's. 200 means its cutoff is 200 kilodalton. So it can separate up to 200 kilodalton of proteins. Okay, if the protein has molecular weight larger than 200 kilodalton, then it will come in the void. So what does it mean? Void means the empty space. So it will not go in the beads, not go in the pores at all. The void volume is only the empty space of the column where there are no bits. Okay, so it will only come through the empty space. So there will be no separation actually. So that is called the void volume. And if your proteins come out in the void, you won't be able to separate them. So this S200 column, for example, this S200 matrix will separate only till 200 kilodaltons of proteins. If you run a protein, suppose for example, one is a 70 kilodalton, another is 100 kilodalton. So these two proteins can be separated in S200 column. Whereas if you this S75 has a cutoff of 75 kilodalton. So if you run a protein which is of molecular weight 20 kilodalton versus a protein which has a molecular weight of 40 kilodalton, then these two proteins can be separated. Also, the limitation of gel filtration chromatography is that if the proteins are of very close molecular weight, suppose 20 and 25, they will not be very well separated in gel filtration chromatography. So that is why for purification of proteins, we often use multiple chromatographic procedures. So it can be like, if you have a protein which has a affinity tag, it can be a nickel NTA tag, 6x histidine tag, or it can be a GST tag. So you can first use the affinity chromatographic procedure, so where you purify the protein based on its affinity. So the matrix will have a particular ligand with which the protein will attach to because of its affinity, and that way the protein can be purified. And then you follow it with gel filtration chromatography, because if you run your proteins only through gel filtration chromatography, that will not also be a good separation. If you only run affinity chromatography like a nickel NTA chromatography, that will also not give you very good separation, right? So we often use multiple chromatographic procedures and club it together one after the other so that your protein can be of higher purity. And the last one was paper chromatography. This is also very similar to thin layer chromatography. So here we use a paper and we put a sample spot, and here also the protein the sample will migrate according to the adsorption, how much it is adsorbed on the surface and how much it has affinity for the mobile phase versus the solid phase. Okay, and there we has this term which is called RF or retention factor. So which is actually the migration of the compound of your interest divided by the migration of the solvent front. So suppose your compound has migrated 18 centimeter and the solvent front has migrated 25 centimeter. So when you divide them, 18 by 25 is your RF or retention factor. Why have I discussed that? Because this also has come in several GATE previous year questions. If you go through them, you will find it out that this RF calculation of or determination of RF also comes as numerical answer type questions. Okay, so this is a very easy thing. Just remember this formula, that it is just the migration of the compound with respect to the migration of the solvent front. So it's just a ratio, right? So now we have also already discussed the answer, that it is going to be C, which is gel filtration chromatography. All right.